This is just a box being hung from a hung from a string. So just imagine some random box, and we'll give it some information. We'll say it's a 5 kilogram box, and that it's being hung from the ceiling of some, classroom or something. And the box is just hanging there. What I'd like you to figure out is what the tension is in the string. All right? Now, I want to start by reiterating that when we do these kinds of problems, Newton's laws can only tell you the size of a force or an acceleration. And they really don't tell you that. They just generate a system of equations. It's your job to use those equations to answer the question. I've given you a set of steps. Let's go through the set of steps for this problem. You guys ready? Step 1. If you can, decide if this is a first law problem or a second law problem. Now, to make that decision, you have to ask yourself, is the object accelerating or is it not accelerating? For it to accelerate, its speed has to be changing. Is this object accelerating or not? No, it's just hanging there. That makes this a first law problem. So I'm going to write that out. Net force equals 0. This is a first law problem. Again, if you don't know why this is a first law problem, perhaps write a note. What did we do to decide if it's a first law problem? Step 2. Draw a free body diagram. All right, we can do that. We're going to draw a free body diagram. There's several steps to doing so, and the first thing is to reduce the shape and size of each object to a single dot representing the mass of the object, or the center of mass of the object. We only have one object, so I'm going to draw a single dot that represents the center of mass of the object. Now on your test, there'll be a box where you'll have to draw in the free body diagram, and the diagram is just a dot with arrows on it that are appropriately labeled. So for us to go and do the next part, we have to add an arrow for each force acting on the object. And I've given you some check boxes to ask yourself which of these forces are acting in our system. Now, we went through the fundamental forces yesterday and talked a lot about them, but at the end of the day, I said there's only one fundamental force you have to worry about. And which one is it? What's that? Gravitational. Gravitational force is always going to be a force of attraction between two masses. In this case, it's the object and the Earth. So you're just going to draw a downwards arrow to represent the force of gravity. However, it is important that you note that this arrow sets the scale for the rest of the size of the arrows you're going to draw. So when you're drawing this arrow, keep that in mind. This is one you know is going to be there for the most part. Now, I do want to put out there that you have to come up with a label. And there's a lot of acceptable labels, but there are several labels that are not acceptable. You can't use a label that is already a letter reserved for some specific or special value. So capital G is not okay here, even though this is the gravitational force, because capital G also stands for the universal gravitation constant. And so they don't want you mixing that up. You also can't use lowercase g, because lowercase g is the acceleration of gravity. You could, if you wanted, use FG or F lowercase g. But if you have 3 or 4 objects, then you might start having FG1 and FG2, and I think that can be pretty cumbersome. I tend to use just the capital letter of the name of the force, weight. This is the weight of the object, so I'll just use a capital W. And that way, if there's 2 or 3 objects, it's just weight 1, weight 2, and weight 3. All right, that's it for fundamental forces. Now I move on to contact forces. And there's a series of steps of things that you should ask. First step, is there a cable or rope or string attached to your object? If there is, then you draw a force that represents the force of tension. This should be an arrow drawn in the direction of the rope or the string. So that's just going to be straight up. Now I'm looking a little bit into the future here, and I'm realizing that if it's just hanging there, there's probably nothing else acting on the object. So I'm drawing that blue arrow purposely to look like it's balancing the red arrow. Because I don't know that I'm going to have to draw any other arrows. But this is supposed to be a system that is in balance, right? So I want to try and make my picture show that too. You'll be judged on that. Now this is a tension force, so I'm just going to give it a capital T. Are there any springs attached to the object? Do we see any springs here? So I'm not going to put in a Hooke's law force. Is the object resting against a surface? Is it on the floor? Is it resting against the wall? No normal force. Is it sliding? Do I have to worry about friction here? No. And unless it's specified, probably not going to hear about air resistance or air drag. Is the object in a bucket of water? Do I have to worry about the buoyant force? No. I think we've reached the limit of the forces that are acting on the object. Now, on a test, this is the end of a free body diagram. You only have the arrows and the dot. But we use the free body diagram to solve the questions. This one's not so tough, but in the future we will. So if you have to do more than just draw the arrows, you should probably do it separate from something that's going to be graded. So on a test, if it says draw a free body diagram in the box, make it just the free body diagram that you put in the box, but then draw a diagram somewhere else to help you solve the problem. So we're going to go on to the next thing, because the next thing says, with your free body diagram, apply a coordinate system to be used to solve the problem. And then you have to go to the next page to know what I mean by that. We are talking about a coordinate system, x, y. And in doing so, there are two priorities. The first priority is to align one of the directions with the direction of the acceleration. Is our box accelerating? No, it's just sitting there. So we don't have to worry about priority number one, which means priority number two, align the coordinate system so that it is aligned with the greatest number of forces. So that suggests to me that I don't make the x direction like this and the y direction like this. Is this aligned with the most number of forces? No, this would be kind of silly, wouldn't it? It'd be better for us to try and align it with the most number of forces, and I don't think I've done that. So let's try and align it with the most number of forces. The plumbing that is connected to my eye wash station is also the same plumbing that's connected to the bathroom in the gym. That's why you hear that. So I put the y direction like that, and the x direction like that. And I'm going to label it negative y, positive x, negative x. Are there any forces that are not along the x or the y direction? Those would be off-axis forces. Are there any that are off-axis? Nope. We are done. We have drawn a free body diagram and applied a coordinate system so we can use that coordinate system to solve our problem. Look, you guys, what do your notes look like right now? Is it just what I have written? If it is, are you really going to be able to reproduce this when I ask you to do this by yourself in a few minutes? So if you need to add something to your notes, do so now. Alrighty. Step 3, apply Newton's law. All right. That means, first of all, we have two-dimensional problems. We need to break them up into one-dimensional parts. So whenever we do that, you take whatever your Newton's law is and you break it up into the net force in the x direction and the net force in the y direction. If it's a first law problem, you set them both equal to 0. Next, we do what the instructions say to do. They say to add up all the forces in the x direction and set them equal to 0. Are there any forces in the x direction? No. All right, good. So nothing to do there. Add up all the forces in the y direction and set them equal to 0. Are there any forces in the y direction? Yeah. And it looks to me like tension is positive because it's upwards. Weight is downwards, therefore it's negative. And I set them equal to 0. This is what Newton's laws do. They generate relationships. You may or may not be able to use that relationship to solve for your answer, but this is what they do. Go ahead.
So let's say if it's not a first law problem and if it doesn't equal 0, it equals something else.
It equals MA, yeah.
It equals, so for, let's say, maybe plus T minus W equals MA. Okay.
We're going to do that right after this one. So now that we've done that, we have to answer our question if we can. Our question asked, what is the tension in the rope? So I want to find the tension in the rope. Which of these variables is tension? Yeah, I think T. So I'm going to solve for T. Now this isn't the answer. This is the beginning of the answer because there are other things that we can be doing. We can do substitution. There are things that these forces stand for. For example, weight is mg. It's the mass of an object times its acceleration of gravity. So I can make a substitution for weight. I can write this as T equals mg. I'm substituting in for the weight. Again, I gave you a list of substitutions. There's several there. So whenever you have weight, it can be mg or it can be that complicated thing to the right. But for right now, it's just mg. We're near the surface of the Earth. That complicated thing to the right, that's when we have like the Earth and Moon, where they're not super close. They're far enough apart where we have to do something different. Now, we're nearly done. We know the mass of the object, it's 5. And we know g, it's 10 meters per second squared. It's acceleration of gravity. Suggesting at the end of the day, to answer our question, it's going to be 50, and the unit of force is the Newton. All good? We'll see. Because now you're going to try a little bit of this on your own. Let's do this one more time. Again, we're just going to change the situation a little bit. We're going to say the motor is going to accelerate the box upwards for a time with an acceleration of 1 meter per second squared. What is the new tension in the rope necessary to accelerate the box upwards? All right. Same set of steps, just repeating it. Let's start at the beginning. Is this a first law problem or is this a second law problem? Second law problem. We were given a clear acceleration, so net force is going to be equal to ma. This is a second law problem. All right, we've done step 1. Step 2, draw a free body diagram that could be used to solve our problem. I'm going to start by reducing our object's mass to a single point. Next, I'm going to draw an arrow representing different forces that are acting on the object. Are there any fundamental forces acting on the object? Yep. So I'm going to draw a downwards arrow to represent the acceleration of gravity. We call this the weight. Are there any ropes or strings connected to the object? Yes. So I need to draw an arrow indicating the direction of the tension acting on the object. But this time, I'm going to draw that arrow to be a little bit larger than the weight. I know the object is accelerating upwards. I need my arrows to look unbalanced. So to do so, I make the upwards arrow more than the downwards arrow because it's accelerating upwards. And I'll label it T for tension. Are there any other forces acting on the object? Is there a surface in contact? Is it sliding? No, I think we're good. So now I want to draw a coordinate system that will help me determine information about the forces. I'm going to align that coordinate system with the most number of forces possible. So that means probably making this the y direction and this the x direction. All right? So We have gotten our free body diagram, added a coordinate system. We are ready to move on to step 3, apply Newton's law. That's right, take this and split it up into the net force in the x direction and the net force in the y direction. Since this is a second law problem, we need to list MA in the direction of the acceleration. What was the direction of the acceleration? Right, that's why I made upwards positive y. I used the first priority, which said to make one of my cardinal directions the direction of the acceleration, and make the direction of the acceleration the positive direction. I did that. So net force in the y direction equals MA. But because we did that, we made sure that the net force in the x direction would be 0. Right, we forced our acceleration to be in only one of our two directions. You definitely want to do that. Now, I know there's no forces in the x direction, but had there been, they would sum to be 0. And only the forces in the y direction would sum to equal MA. Since there's nothing in the x direction, I'll kind of ignore it. In the y direction, I have tension upwards, so it's positive. Weight downwards, so it's negative.
Again, pardon this interruption. At this time, we'd like to release to the pep rally the members of our cross-country.
Let's see if we can get a little bit further here. I want to get tension by itself, so I'm going to move weight to the other side. So this is really step 4 where we begin to solve the problem. Bye, guys. So tension equals MA plus W. I just added weight to both sides. All right, so we're going to do the same things. We're going to do substitution here. I'm going to substitute mg in for W, and we'll get tension equals MA plus mg. We know the mass, it's 5. The acceleration was 1. The mass, again, it's 5, and this time it's g, which is 10. And it looks to me like it's going to be 5 plus 50, or 55 newtons. Any questions? Now look, I know you guys. You're looking at me going, Mr. Sheldon, this is ridiculously easy. Please, don't be complacent about this. I'm starting as easy as I possibly can on purpose. Now, I want you to hear me out here. The tension is 55 newtons, and the weight was 50 newtons. What was the net force on the object? 5 newtons. The net force was 5 newtons. It was 55 upwards and 50 downwards. So the net force is 5. But we also could have gotten that right here without doing any work at all. I want you to pay very close attention. If I had asked for the net force, you didn't have to do any of this, because net force equals MA, and the mass was 5, and the acceleration was 1. You could have gotten the net force without doing any work, because it had to be 5 newtons. You see what I'm saying? Finding an individual force takes all of this. Finding a net force sometimes can be super easy. So if you see a question, especially on multiple choice, that says find the net force, there might be a speedy way to get to the answer. Do you see what I'm saying? Sure? All righty. Let's see if you guys can do this on your own now. All right? I'm going to change the problem just a little bit to make it a little fresh, but not much. How many of you are big fans of Pep Rally Day? I like them. They're okay. They're fun. I have to participate in this one, but just a little bit. All right, imagine I have an elevator. The elevator is connected to a mechanism by a rope or cable, and you are inside the elevator. Now, let's say you have a mass of 75 kilograms. The elevator is going to lower you to the ground with an acceleration of 2 meters per second squared for a short time until you get to your operating speed. What's the force of the elevator on you as you accelerate? Okay, again, you're standing in an elevator. You have a mass of 75 kilograms. The elevator is going to accelerate downwards to 2 meters per second squared. What is the force of the elevator on you as the elevator accelerates downwards? Write that down. This is a second law problem, starting from the standpoint that the net force will be equal to ma. I'm going to go ahead and draw the arrows representing the force on my person. I'll reduce the person down to a dot. Is the person experiencing any fundamental forces? You guys have to make this judgment call. Are they experiencing gravity or not? All right, so I draw an arrow representing gravity. The person experiences a downward force due to gravity, and I'll label that the weight. Is there any string or rope attached to the person? No. I've been in a lot of elevators, and I've never had to hold on to a string or a rope. Have you? I think the string or the rope is attached to the box, but I stand inside the box. Don't you guys? All right. So, is the person in contact with any surface? Yes. So I think we can probably say that there's a normal force on the person from the floor of the elevator. Does that make sense? In what direction would I have to draw that for it to be perpendicular to the floor of the elevator? Now, perpendicular means at a right angle to the floor. So I think it's going to be upwards. You guys agree? So I will draw an upwards arrow, and I'm going to purposely draw an arrow that is smaller than the weight because this person accelerates downwards. Because they accelerate downwards, I know that it has to be an unbalanced force. So I'm going to label it normal, but I'm making sure it's less than the weight. I think that's it. Is there any, are they sliding? Are there any springs involved? Is the whole thing submerged in a bucket of water? So I don't think any of those other forces have anything to do with this. So I need a coordinate system. My priority is to draw a coordinate system that is aligned with the direction of the acceleration. What direction is the acceleration? Downwards. So I'm going to draw a coordinate system where positive y is downwards. And that means upwards is negative y. I'm lining it up with the direction of the acceleration. Of course, this makes the x direction this way. All good? We now have our coordinate system. We have our free body diagram. It's time to move on to apply Newton's law, which means taking this and breaking it up into the net force in the x direction and the net force in the y direction. In which direction is the object accelerating, x or y? So I'll put ma in the y direction and 0 in the x direction. Are there any forces in the x direction? Is there any force pointing to the left or the right? I don't have to worry about this. Are there any forces in the y direction? Yes. And we've made downwards positive. So weight is positive. Normal force is negative. And that equals mk. Any questions yet? I know it makes sense, but it's hard to do when you're on your own. This is all that Newton's laws do, but if we want to solve the problem, we want the normal force. So we need to solve for that by itself. So I'll start by adding it to both sides of the equation. And then I'll subtract ma from both sides of the equation. Now, what could I do next? I'm trying to figure out what normal force is.
Just do weight for mass times gravity.
Yep. Perfect. And now I have stuff, right? I can plug stuff in for M and G and A. So 75 times 10 minus 75 times 2 equals the normal force. That looks like 750 minus 150, which I think is 600 newtons. The floor delivers 600 newtons. My body is 750 newtons. So I feel a little lighter when the elevator starts to accelerate downwards. You guys have all been in an elevator. You know that when it just starts to go downwards, you feel a little lighter for a second. Well, that's what's happening.